Inside high-density warehouses, robotic vehicles navigate massive grids, tasked with retrieving thousands of items a day with no room for error. This floor plan shows the core routing problem. The objective is to find the single most efficient path from a starting coordinate, usually the top left, to a destination at the bottom right, picking up the maximum number of items along the way. To prevent gridlock in these narrow aisles, movement is strictly constrained. The robots can only transition in two directions. They can move right, or they can move down. Finding the mathematically perfect path under these limitations determines the total throughput of the facility. A perfect route maximizes output. A calculation error leads to total supply chain failure. The most direct approach to solving this is a recursive brute force search. The system looks at its current position and attempts to calculate and verify every possible future path all at once. Looking ahead at every intersection creates a massive computational load. Each decision branches exponentially, exploding into millions of overlapping paths. This time complexity, O of 2 to the power of m plus n, means every additional shelf doubles the computing time. When the CPU spikes under this load, the system halts. The robot receives a timeout error and freezes mid-aisle, blocking the entire picking lane. Relying on future prediction algorithms for routing causes these systems to crash as soon as the grid reaches industrial scale. To keep the robots moving, system architects move away from prediction and toward a structured technique called dynamic programming. Developed by Richard Bellman in the 1950s, this approach breaks a complex problem into optimal substructures. Instead of solving the whole grid at once, you solve small, overlapping subproblems. The shift is in the logic. Instead of guessing the future, the algorithm builds the optimal answer iteratively, square by square, from the ground up. By replacing recursive prediction with sequential calculation, the routing process remains stable, even as the warehouse dimensions increase. In this 2D matrix, the value of any given square depends only on its immediate neighbors. The algorithm compares the yield of the cell above and to its left, adding the current items. It systematically fills the entire grid row by row, never recalculating a visited square. This drops the execution time to a polynomial rate of O of m times n. The calculation happens in milliseconds, allowing the robots to move without interruption. However, storing a fully populated 2D matrix for every robot in a massive facility creates a new bottleneck. It requires a significant amount of memory to maintain that data for every active unit. While 2D tabulation prevents the CPU from crashing, the spatial overhead of these massive grids prevents the system from being truly efficient. The final refinement used by senior architects is space-optimized 1D tabulation. The 2D matrix contains a hidden redundancy. To calculate the current row, the algorithm only references the row immediately preceding it. Keeping the entire history in memory is unnecessary. Once a row provides its data, it is discarded, collapsing the matrix into a single 1D array. This relies on directional computation. Moving across this single line, the system updates its values in place, reusing the same memory addresses. Collapsing the matrix changes the constraint from a multi-dimensional map to a streamlined mechanism that reuses its own state. The result is a space complexity that plummets to O of the minimum of m or n. At this scale, millions of routing dependencies are flattened into these linear rules. The hardware processes the pathing data sequentially, removing the need for high-capacity memory banks. This translates directly to performance on the floor. Robots execute turns and pickups with zero hesitation, operating at the physical limits of their hardware, because the software is no longer a bottleneck. By mastering 1D space complexity, engineers ensure that even as warehouses double or triple in size, the routing logic remains lean enough to run on standard hardware, guaranteeing long-term operational scalability.